Okay, shall we start? Not so many people today. Okay, a bit confusing with the screen recording, since if you record the screen and you stop, you just see your screen. But the last recording worked, but I had a flu starting from last lecture to up till now roughly, so I haven't uploaded it yet, but I'll do that try to do it this afternoon. Same thing here, so I hope this works. For the last lecture, the screens didn't move, the slides didn't move after the break, but otherwise everything is there. So I already got requests. First, are there questions about last lecture? No? Okay, so today we'll discuss biomolecular simulations. So this is a topic which is not in the book, but you'll practice this in the computer labs next week. So you'll get to play around a lot more with it. So today we'll discuss the basics of molecular dynamics, then in particular aspects relevant for biomolecular simulations, which is mainly proteins, but also DNA, for instance. Then comparison with experiments, molecular mechanics again, which already got introduced by Eric in the first few lectures. Go back to that. Then we'll discuss a bit studying equilibrium properties and dynamic, and then sampling conformational transitions, which we discussed last lecture. But now, how to do that with molecular dynamics. So last lecture I finished off with this movie. So this is nice to illustrate the power that you get from molecular simulation, so you can really see all atoms move in all detail. So you can see anything, and you can anytime you want, you can just press stop, and you can analyze. Particularly here it's a bit blurry, but it's probably because of the movie. I mean, you can see where atoms are. You can see how they interact. You can even compute forces between atoms if you would want to. That's usually not so relevant, but you can look at anything you like, and you can also modify anything you like. It's running on a computer, so you could artificially change things, which might not correspond to real life, but you can see what the effect would be if something would be different. Or you can change a residue, or you can do other things, obviously, as well. So there's more on top of here. It's the Markov state model, which is shown here, which I'll shortly discuss as well towards the end of the lecture. Okay, so how does this work? So, yeah, apologies, I copied several, especially formulas from another presentation, but which has white with a black background, and I couldn't find a quick way, especially with a fever, to figure out how to make the formulas white. So I hope they're visible. Okay, so the basic of molecular dynamics is really simple. So this is just given n particles each with a mass and a potential v. That's the function of the coordinates of all these particles. Molecular dynamics is basically just Newton's equation of motion. So mass times acceleration equals the force, and the force is minus the gradient of the potential. Yeah, that's standard, very standard mechanics. So one could think there's not more to it than this, but as you'll see, there's a lot more to it, especially because proteins are complex, as you've learned over the past weeks. So simulating them is not so easy, but this is the basic equation is really simple, so this is not much more to it than that. Then there's a lot more about actually what you're sampling here, what you get out, how accurate it is, and so on. But the basics of setting up such a simulation in the physics here is really, really simple. So you understand Newton's equation of motion. So basically let's see, or do I have that on the next slide? Yeah, right. Yeah, the next slide has. Yeah, here. So one question is how to integrate this. This is actually not so hard. So for people having taken a simulation and modeling course, you know you should use a symplectic integrator, but that's about it. So they're really simple, and any tool you use will have that. So that's not the hard part. The most critical part here is often the quality of this potential V that you have. So obviously, this equation, what's going to happen? Well, you can change the masses, but that won't have much effect. I mean, things move a bit faster or slower. But obviously, the sampling will happen according to this potential V here. So this is extremely critical. Yeah. So what kind of system you're simulating is set by this V. Yeah? So if I'm simulating an argon gas or a protein or a metal or so, is all governed by this potential. Yeah. So everything is hidden in here, basically all your model. Apart from how many particles I choose, and again, yeah, the masses, but that don't just affect the kinetics, not the actual distributions you get out. So this is a very critical here, and there's a lot of effort going into this, and you have to be very careful with choosing that. So I'll go into more detail on this during the lecture. Then another aspect is how to choose the initial coordinates and the initial velocities, but often those are not so critical, as you'll see later. So you need to start from somewhere, which is if you just have a gas of molecules or a liquid, it's not so hard. I mean, you just need to generate some uniform distribution, which is roughly okay, and the system will equilibrate. But if you have protein structures, you see, I mean, you've seen these folding landscapes, and so you should start at the right point to get somewhere. Huh? And you can't simulate very long, which is the other issue. So if you don't start close to where you want to be, you might never get where you want to be. So this is a major issue, especially in biomolecular simulations, because you need a pretty accurate structure of your protein, or whatever you're simulating, DNA, RNA, since it will often not get to the native state or the state you want in quick enough time. So it's not a magic tool that gives you, imagine the folding problem again. If I start with an extended protein, fully extended, it won't magically get you towards the native state. So this can be also very, very critical. You need some usually experimental structure. Now there's a PDB data bank which has, I don't know how many thousands, 10,000, 100,000 structures in there now. So if you're lucky that the protein you want to study has a structure in there and it's a relevant structure, then you just get it from there and then you're done. But if you don't, then you have to do a lot of work. So this can often be problematic. And then, we'll go towards the end of the lecture into how long you can simulate, because this is limited by the computational resources or how much computational effort you want to spend. So even though we can do billions of steps, that's often not long enough, as you'll see. And you need good tools for that, but I think that's a bit beyond this lecture. So that's one of my main things I work on is the GROMACS molecular simulation package, which is likely the fastest in the world. Because of this issue, that's pretty important. Okay, so what aspects come into play here if you look at molecular dynamic simulation? So, one which I already discussed is how to integrate the equation of motion. That will be on a slide further on. Then it's how to set up a force field, this potential V. So hopefully you can choose some force field from somewhere based on evidence that this has worked. But if not, then you're, as we'll also discuss later, this is going to be problematic. So this could be a lot of effort. How to set up initial conditions. Then there's the question, how long should I simulate? I mean, that's might be hard to answer, but it depends on what you want to see and what timescales you expect you need to cover for that. But that's an important question if you need to set up a simulation. Then one could ask, what output should I write? I mean, in principle, you can write every time step every 2 femtoseconds, but then you'll quickly fill up any disk. I mean, how many terabytes you have, you'll fill it up. But that's often not interesting because the system just wiggles around. So you're not interested in that. You're interested in the interesting events. So you don't need to write too often. But if the interesting event is very fast, like you want to capture a transition state, for instance, where it flies over very fast, then you might miss it. So you might need to write out very often, or you need to have magic code where you can go backward in time and write more often, which with some codes is possible. We would like to have this, but that puts very high requirements on the way you set up your code and you run it. So that's a bit tricky. Then how should I analyze the results is also a very important part. So for some things this might be simpler if you're just looking at a gas or so, or a liquid, but although you also already have to be careful there. But as you've learned by now, proteins are very complex, so you need to know a lot about your protein to actually make sense out of it. I mean, there's still people around, scientists, that think like, I just simulate. I just take this protein, I'm interested in this, or I'm working on this, doing experiments or so. I put it in an MD package, I run it for some nanoseconds, and then I publish the result. The protein moves from here to there or so, but that doesn't tell you much. I mean, you need to have a question. Or, well, something very interesting needs to happen, and then you need to analyze this carefully. Why does this happen? Is it reliable? So this can be setting up simulations by now. If you don't have a problematic case, actually rather easy. So often most of the effort goes into analyzing. What do you want to get out of it? So if you have a clear question, it might work. You can answer the question or not. But often the interest exactly with molecular dynamics is simulating systems which you cannot study experimentally. So there might not be so much known. So you need to figure out, is this realistic what's happening? Is this relevant? Did I end up in a state which is actually a relevant state, or am I far away from it? And how do I analyze that? So that requires often a lot of biological or biochemical knowledge about your particular system. which relates to are my simulations reliable, which depends on the force field where you started and how long you run and so on. Then often you might realize my simulations are not reliable, I didn't simulate long enough, so then the question is how can I maybe sample faster in some way? There are lots of tricks there, which we're also working on. And then there's a separate aspect of how to develop efficient algorithms. So if your code is not fast, or you're using some code and then you realize that, for instance, GROMACS is 10 times faster, which is easily possible, then you're like, well, you can try to improve the code you have or so, but you can also look for other codes that are much faster. That might give you 10 times more sampling. So there are a lot of aspects here, and if we look, here it requires actually a lot of different expertise. So before I was in the theoretical physics department, and I'm still collaborating with people there who are now in the physics department. And there the focus as a theoretical physicist is for instance, on sampling methodology. So that's, you don't care so much about the actual protein, but you care about complex problems that need smart solutions. So that's one aspect which I've also worked on together with people from the theoretical physics department. Then on the other end of the spectrum, you have biologists which might not want to care about all the physics and everything. They just want to know, how does my protein behave? I mean, how do I learn more about it? So then, you need to be able to set up simulations and run the analysis and rely on work that others have done to make that go. So the force field and the tools. And then, there's the aspect of who makes the tools. So efficient simulation, analysis code, for which you need people like computer scientists almost, but those are often not interested in actually efficient code. They're just interested in how do I make my algorithm instead of order n squared, order n or so. So it's actually hard to find people that are interested in making code fast. So you need to be a bit nerdy to a certain extent. So I've done a lot of effort here. And we have some smart people in our group that do that. So that's often not the high scientific interest because you're often just improving the prefactor, although we have a lot of smart algorithms that we're publishing. But on the other hand, this has a lot of impact. I mean, this is the reason why GROMACS is used by, I don't know how many people over the world, is it 10,000? We can't count because it comes standard with scientific Ubuntu or other distributions, and it comes installed everywhere. So we don't know how many people use it, but there's a high reward in that sense. And then there's the other part, which is also very elaborate, is making the force fields, which can take a whole group many years. And that doesn't bring you much while you're doing this, especially as a PhD student, for instance. But later on, it might give you hundreds or thousands of citations if the force field turns out to be good and many people use it. So that's also an enormous effort. This is more towards chemistry, so to figure out how to best represent the interactions between the different atoms, as you'll see soon. How that works. So there's a wide range of different expertises needed in this field. And all these people are needed. So we are lucky that the group I'm in together with Eric Lindahl and Lucy Delamotte, we have basically all these type of people in our group. So we have a large coverage, which is very nice. So people can talk to each other and they can help each other. And we can understand what the needs are from the biology point of view and use that to make our codes better and our sampling algorithms. And always people coming here, they need to learn something from somewhere. So if you're from physics background, if you need to see this course already, you need to learn about biology, and then you might need to learn a bit about how simulations work and how the tools work. So, but everybody needs to learn here, so from wherever you come. And it's nice to have a mix of people for learning from each other, also for the fun. Okay, so then before actually starting, let's discuss when to do simulations or not to do simulations. So let's start with the negative point. So first, simulations can be, well, it's getting easier and easier, but they can be tedious to set up and they can require a lot of computational power, and then, the reliability of the result is always the question. I mean, you might question it yourself, or you might think you've done a great job, and then the reviewer is an experimentalist who says, this simulation, I don't trust anything. That can happen. Before starting, these are always things you need to worry about. So some people are very enthusiastic, especially if they've never done simulations before. They think like, this is a magic tool. You just press a button, you get a beautiful movie like I showed, and then you can see everything. But everything you see is just as accurate as the model you've made. So the question is, how accurate is your model, and how much did you sample? But on the other hand, they do provide dynamics in full atomistic detail, and that's something that no other method can give you. So X-ray or crystallography or cryo-electron microscopy can give you a single structure in atomistic detail. with an enormous amount of effort, but no dynamics. There are some experiments which can give a bit of dynamics, but those are usually very coarse. You just get one variable, one spectrum for a whole molecule or so. Whereas here we can see everything. So we can see x, x as a function of t for whatever detail you want. So that's enormously powerful. You can get information on nearly everything. Since you have the coordinates as a function of time, you can compute any quantity you want, because any quantity that's relevant except for quantum mechanical kind of things, for which you need more detail, you can compute from this. So if you can cover the time scale. So you can compute anything you like. And yeah, you can easily change conditions, initial conditions, boundary conditions, solvent. You can change whatever you want just by playing around. That's just how easy your software is to set things up. You can modify stuff, which in experiment can be much harder. So that's also a big advantage. So you can easily modify things, like see why are things going as they go. Is it because of this or because of that? And what happens if I change the conditions, if I change the temperature, if I change the solvent, if I change the composition of the membrane, if I change whatever. So that's really nice. So if we have a look at the experiments that are relevant for the same field. So first there are thermodynamic measurements. So those are things like phase diagrams, densities, heats of vaporization. So those are physical chemistry kind of measurements. So those are very important for usually liquids or gases, so not so relevant directly for biomolecular simulations, but those are relevant for parameterizing the force field, because you can measure these extremely accurately. So if you need a water model, or you need small molecules, or even a whole protein, if you can decompose it in side chains, for instance, and you can make solvents of those, and then you can measure. So this is a very valuable experiments here that can give you very accurate numbers. So that's good for checking, or for building your model and checking it. Here. But then for biomolecular experiments, so we have, I've mentioned a lot X-ray crystallography, so that gives atomistic detail about static structures. So this is still where most of the structures come from that are used in studies in the field, but also for input for biomolecular simulations. So this is very highly detailed, but very resource intensive, and may be affected by the conditions, because you work at very low temperature at very packed structures, not the cellular environment as has been mentioned before. Then there's nuclear magnetic resonance, which is not so much discussed in this course, I think. So these give some average atomistic detail and some average dynamics in some way. So you can get a bit of dynamics. You can get accurate structures, but it's also very resource intensive, and there are size limits. So the protein can't be too large here, because you have to decompose the spectrum. And if you get more and more residues, the spectrum gets more and more dense. So it gets more difficult to disentangle. And you need to cross map things. So this is still used, but for smaller molecules. Then there's more and more single molecule experiments coming. So that's nice, because then you can actually see how a single molecule behaves instead of a whole ensemble of molecules. But obviously, that's the resolution and the number of observables is not going to be very high if you do that. So you need to pull on a molecule or do something special with it. And then, the thing that has come up the past decade or so is cryo-electron microscopy. So this is atomistic detail for medium to very large size structures. And this can't go to very small sizes. But this is turning out to be easier than X-ray crystallography in terms of making samples and also in terms of solving structures. So this is where a lot of our structures are coming from now, especially for membrane proteins, which are quite big and difficult to crystallize often. So here you can just image them in the membrane, which is much nicer. So you just overexpress, you have a lot of proteins in the membrane, you take a lot of pictures. But again, this is static, although here you get pictures of many different, so you in principle get pictures of the whole ensemble, but then you need to, since the pictures are so blurry, I don't know, did Eric show pictures of cryo-electron microscopy structures? So you need to average over 10,000 of pictures or so to get something slightly where you can see some structure, ideally 100,000 or so. So you can imagine if I have say 5% of 95% of one state, 5% of the other state, the 5% state you probably can't resolve because there are too few of them. So you can see major states that are there, but not minor populated states. Okay, but as you see, molecular dynamics is very complementary to these things. So you can get detailed information on detailed atomistic lengths and timescales, which none of these methods give. But on the other hand, the reliability can be a problem. So if you can verify the states that you sample with the important states that are observed experimentally, this is a very nice complementary thing of having any of these experimental techniques combined with molecular dynamics. So it used to be when I started in this field a bit more than 20 years ago that molecular dynamic simulations were not accepted. So X-ray crystallographers, for instance, they would say here that a protein is one structure. Look, what comes out of our experiment. So MD can't be right because it moves. So it moves away from the crystal structure, so it's wrong. So that was for a decade still a big problem. So you would always have to hope that you didn't get an X-ray crystallographer as a reviewer for your paper, which of course nonsense because they put their structure at 0 Kelvin. So how can they ever know if the structure moves or not, right? It can't move because otherwise they wouldn't get a crystal structure. So the crystal structure has to be 1. Otherwise it wouldn't crystallize and they couldn't solve the structure. So things are much better now in that sense. So now it's actually the other way around. So if people want to publish X-ray structures in Science or Nature, they're often the question, well, could you do an MD simulation? Because how does it move? I mean, do you have any crystal artifacts because of contact or so? So now it's the other way around, which is on the one hand nice, but on the other hand you just get questions from X-ray crossover, give us an MD simulation. It doesn't matter what, so we just need to write there that we did MD. So, or they want to do it themselves, which you can run anything, but the question is how useful that is. So, it's now since a decade or so it's widely accepted that proteins actually move. I mean, you've seen many movies and there's experimental evidence with different techniques now that show that proteins move. So, and they have to move for function, as we also show. So it's good to look at dynamics. Okay, so if we're going back to molecular dynamics, so some basic considerations here. So we try to calculate paths or trajectories of individual particles, which are of course coupled. So we know that there are errors in these because of the model and because of the integration. So how do you make sure that your results are reliable? Well, the main thing here is that in any kind of sense is that errors should not add up systematically. Then the averages should still be okay. Yeah, that's how things work here. So we make a lot of errors in this, both in the model and in integration. But this is a very complex issue and this is very difficult to figure out. So you often can't be guaranteed that errors don't add up, like especially in the force field. If I have many atoms of the same type interacting, so if I'm off for one pair by a very small amount, a very small fraction of the thermal energy, I can easily have thousands of those interactions, 10,000, 100,000, so those add up. And the error, of course, if you make an error in one pair, with the error being some pair being slightly too attractive, then all of them will be too attractive, right? So these errors can easily add up. So that's a big problem. So especially the force fields are critical here. And you have to be careful with the integration, but that's a roughly solved issue there. So there we can make sure that they don't add up, as we'll show later. And then the question is, how do we calculate motion here? Well, that's through integration. So that's, let's start with that. So the integrator we use is the leapfrog integrator. There's also velocity Verlet, but that's basically the same. I won't go into details here. We have other courses on that or you can look it up. So the leapfrog integrator is the simplest to show here. I won't show any derivation. This is basically done, there's a delta T missing here, I see now. This integrator you basically get by, you can expand forward or backward, do Taylor expansions here. But the trick here is that, it's also why it's called leapfrog, is that, well, we separate, as usual, we separate the second order differential equation in two parts. So one equation for the velocities and one for the coordinates. So the velocities get integrated over one step and you add in the acceleration times the time step. So that's a very simple first order integrator in principle. But the trick here is that this is offset by half a time step. So you go from t minus a half delta t to t plus a half delta t. And then the coordinate integration here, the delta t missing here, but it's the same first order integrator, but there we're now at the full step and we integrate with the half step velocity here. So the idea is, I should have put in the picture, but I can draw it on the board. So the idea is that I have x here, and I have v here. So I integrate v like this, and then I integrate x like this. And then I have the acceleration here to add up here, a times delta t here, which comes from which takes in the coordinates. So the idea, there is a more fundamental thing, is that this integrator is symplectic, but what you can already see here is that this is you can simply change these arrows around, and then I would get the same integrator but running backward. Yeah, so that's a simple way. That's not the full thing here, but that's one simple way of seeing that this integrator is very nice. So you can change t to minus t, and you would get the same integrator. Yeah, that's not the guarantee that things will work out, but this is a needed property if you want to conserve energy in the system. So if you go forward and you go backward, you get the same results. So that's if you want to conserve energy, which is very important in these kind of cases. That's what you want. If you go deeper into this, it actually turns out that this is a symplectic integrator, on which I think I don't have now in this course. I skipped that. I have that in the simulation and modeling course. So that means that it actually conserves phase space volume, which means that if I start out, let's see, can I draw that easily? Let's see. If I have x and I have v, and I start out with a small area here, then if I start out with different points here, they would end up in a volume here, which is the same if I go from t to t plus tau, for instance. Then these volumes don't change. So that's what a symplectic integrator does. So that means that if I have points close together in phase space, so I perturb my conditions a bit, then the points don't diverge or they don't converge to one point. So that's a symplectic integrator. So this is a wanted property if you want to conserve energy in the system. And a symplectic integrator would actually conserve not the exact Hamiltonian of the system, but a shadow Hamiltonian. So a Hamiltonian is very close to the original one. This goes a bit too far, I think, for this course here. But that's the reason why we choose this leapfrog integrator or velocity relay, which is basically the same. So this conserves energy. So this makes sure that errors don't add up in a systematic way. So we make errors every integration step, but actually, so these integrators themselves, they're only let's see, they're only, what is it, first order by themselves? Yes, huh? Second order, let's see, no, there's an order delta t squared here, but if you make a time step smaller, yeah, you get more steps. So in principle, they're only first order, both. But the energy conservation is perfect here, so there's no error there. And then the whole integrator is, what is it? It's third order, I think. So this is highly accurate, even though the scheme is very simple. But if you slightly change this, then things go very wrong. So there's an exercise in the simulation and modeling course I give where you see that if you slightly change things here, then things explode. But you see that this is really simple. So writing a code that does this is trivial. So you can write an MD code, as long as the potential is simple, you can write that in a few minutes. It's not hard. This is basically all there's to the integration, apart from thermostats and barostats, which I'll touch upon later. But yeah, you can write a code basically in 5 minutes, I'd say, if you know any coding language, any programming language. So that's very nice. So we have that covered. Although there's a lot of deep math behind these things. So there's still work going on here. So not everything is fully solved, fully understood mathematically. Okay, so then let's turn to molecular mechanics. So I think this has been discussed a lot, probably what's in the first lecture or the second lecture by Eric. So this is basically the model we're using in molecular dynamics. So this is, the term here comes from when the computers weren't powerful enough yet to do full simulation, so you would just compute energies. So the idea here is that we make, as has been said in the first lectures, we make the model as simple as possible, but not too simple that things don't work. So we model atoms as point-like particles. we use an empirical approach, so we adjust the model to fit reality also, not theory. So you could fit to quantum mechanics, but that's not accurate enough yet. This has also been discussed by Eric, I think. We hope to get there in 1 or 2 decades, but that's still not the case. So there's still, you would think quantum mechanics would be very accurate, but there are many things like dispersion, and there's other things which are not very difficult to get there. So whereas reality, like these physical chemistry measurements, they can be accurate up to, I don't know how many decimals. It's insanely accurate, so you can't get much better than that. So you can fit to that to reproduce exactly those properties. So yeah, the goal here is also to predict real structure and motion, not explained from first principles. So there are some studies which try to do that, but that's a different goal here. If we try to model proteins, predict them, then we're not interested in understanding from the quantum mechanics up how this works. We'd like to know simply how they work in whatever way is scientifically reasonable. Yeah, so for instance, here's a simple example. So we adjust the size or the radius of atoms to reproduce the density instead of computing it from quantum mechanics. So already the Lennard-Jones potential, as discussed earlier, is already an approximation. So you don't care what the sigma is there as long as you get all the physical properties that you can imagine or that are relevant right. Of course, it's good to have roughly the physics correct. Otherwise, it's hard to if you don't have any physical models, so there are other approaches which there's becoming popular now, like for instance machine learning or so. So that works to a large extent, but it's very tricky because if you don't have any physics in it, then as long as you end up outside of the conditions where you have checked things might go very wrong. So it's good to have a basics of physics, because then at least, even though you parameterize only on a subset of configurations or states, you have a reasonable expectance that it will work also under slightly more extreme conditions, like if something gets compressed or atoms that you haven't thought might interact, they would actually interact. Okay, so then let's have a look at the units we like to use. So these are popular units. You can use any unit you like, but you would rather not use SI units here in this case, because you see here that there's some numbers that turn out very small. Huh? So length is a nanometer is convenient. There are other units here, atomic units or whatever, but it's nasty, difficult to convert to SI. Time, we like to use picoseconds, 10 to the minus 12. Then mass, for instance, it's 10 to the minus 27. So you already get problems if you would do that in floating point numbers in double precision. It's probably okay, but in single, you have to be careful. So of course, you rescale things to reasonable units, which is this. So if you do this, then you can get energy as mass times length cubed divided by time cubed, and that turns out to be 1 kilojoule per mole, which is really nice. So, so that's why we use these units here, because the energy turns out nice here at once. So a kilojoule per mole is a convenient unit which is used in Europe for expressing energies of molecular systems. In America, they like to use kilocalories, but they need to convert. There's all kind of, I cut and pasted this, but something went wrong with the exponents here, sorry. So mole, but you know the number, I guess, is 10 to the power 26 times 10 to the power 23. So then we have charges, electron charge. So you could use length angstroms, which is 10 to the minus 10 meter, but that's inconvenient since it wouldn't give this nice energy unit. And kcals, which give this conversion. Those are also popular units. But that gets tricky in your code, since you now need to know if you compute an energy, when is it in which unit, and that gives a lot of bugs. So I'd like to avoid that. Okay, so then discuss atom types. I don't know, no, I think Eric didn't discuss this in his lectures. So atom types, you might think this is really simple. So organic molecules, they mostly contain carbon, hydrogen, nitrogen, oxygen, sulfur. And then I only need 5 atom types. You think that's simple. But actually that's not the case, because that doesn't account for the electrons moving between the atoms. So recall we described atoms as point particles with also basically only interaction between the points there. Whereas in reality we have electrons moving around that interact in complex ways. So that means, for instance, that an oxygen here in water behaves very, very different from an oxygen in an oxygen molecule. Yeah, so you can't use the same interactions for that. Same kind of thing with carbon. So you could have a non-polar carbon, like here in a protein, aliphatic type of carbon, versus a carbon in an aromatic ring. Those will also behave very differently due to the electron distributions here. So this means you need different descriptions of these different atoms, and then you quickly end up with hundreds of different atom types, unfortunately. or maybe I don't know, force fields which can do a bit less. Depends on how you represent them. Yeah, so one thing to note, for instance, is that the oxygen in water is very polarized, so they'll be in charge of around 0.8, depends a bit on the model. Whereas obviously in this oxygen molecule, they're neutral since it has to be symmetric. Yeah, so those are very big differences. And this also affects how you would have the Lennard-Jones the van der Waals interactions. They would also be affected by this. So if we look then what happens in how this is done in practice. So here are some examples of different side chains, and here the atom names here are the atom types in a force field. I forgot actually which force field this is. So we have CAs, we have CTs, do we have more Cs? We have normal Cs here. Then we have a backbone C, which should be different again. No, it's a C as well, this one. We have different O's, an O and an OS, and then they all have different partial charges. So there are different atom types for the different environments, different chemical environments, different moieties. And on top of that, each atom is individually, each charge, partial charge of the atom is individually parameterized, usually from quantum mechanics nowadays, which is quite accurate for doing that, although with some approximations. So this way you don't have too many atom types, because there's things like an aliphatic carbon, aliphatic carbon in the chain here, for instance. There's a tetrahedral carbon here. There's an aromatic carbon, and there's a carbonyl carbon here. But then you don't need different atom types for all of these 6 different ones, even though they all have different charges. So that's doable. So you just need to parameterize a few, and then you get the charges from quantum mechanics. That's how things usually work. But you can see there are a lot of parameters in here. Yeah? It's not something that you could guess or so. And these things matter a lot, because these small charge differences, the Coulomb interaction is extremely strong. So it has a very large prefactor. So changing any of these charges by a few percent can have a very large effect. So it's not something you should get wrong. So you have to rely on the people that made these for you, that they're good. Here's something disappeared. Okay, so let's recap non-bonded interactions. So these are interactions between all atoms through space, although not the nearest neighboring ones. So they take care of the packing effects, so that things pack in the right way, so that they don't overlap. No, there's Pauli exclusion, but there's also that they attract each other through van der Waals interactions. I'll have the equation later again. So this is basically what we use Lennard-Jones and Coulomb, as Eric has introduced. I'll get back to the full equations later. And then electrostatics, obviously, as well. So especially in water. So water is a high dielectric liquid. So that has a lot of effect on electrostatic interaction. So how charges interact depends a lot. So there are some charge residues in proteins. Although, let's see, if you go back here, there are also things with partial charge. These charges are very small, so they don't have much effect. But if you have a charge residue, let's see. Do we have one here? Yeah, here. This nitrogen, this residue with +1 charge. So these atoms will have higher charge, so they interact here strongly with other charge groups, and that is mediated by the water. So this is these non-bonded interactions are a very important part of the model and very critical. So these have to be parameterized very accurately. So what we have then, so I won't go, I'll show the equation on the, let's see, yeah, I have the equation on the slide after. So Eric already introduced bond vibrations, angle vibrations, torsions. So those are the most important. There's also an out-of-plane torsion, which I haven't drawn here. And then we have van der Waals interactions and electrostatics, and those are basically the 5 most important, or that's everything already, I'd say, except for the out-of-plane torsion. So these are the things we model. So it's not much. But the problem is that there are many parameters involved. So also these angles and the torsions are very critical. As you can imagine, if I change one torsion, then the whole rest of the molecule moves around, in principle, around that. So these are also very critical. And there are many different ones because they depend a lot on the electronic distribution in the chain. So again, there's a lot of parameters going in. But there are not so many interactions. So if you need to write a code again, I mean, you just need to implement these 5. So there's an out-of-plane torsion, but it's the same function as this. You just number the atoms differently. So if you need to write MD code, you need the integrator, and you need to compute these 5 interactions. It's actually not hard to do if you don't need very efficient code. If you need efficient code, then you can have a whole team working on this for decades, as we have. Okay, so what we have then is, here's the full, I hope, yeah, it should be just visible. Here's the full force field. So now we have the simple harmonic bond interactions here. With force constant, we have the harmonic angle interactions, which look the same, except that an angle goes in here instead of the angle difference instead of a distance difference from the equilibrium angle. We have the torsions, which you could write as a set of a sum of cosines, for instance, which have parameters here for every term in here, for every number of periods. And we have impropers, which are basically the same as torsions, but they're harmonic to keep things flat in case you need that. Then we have electrostatics, which is Coulomb's law, just Qi Qj divided by R. And then we have the van der Waals interaction, which are modeled by Lennard-Jones here, which is also a very simple equation. Yeah, so also this is a bit more than 5 minutes to write in code, but doable in the afternoon, I'd say. So, and not so hard. So writing, actually having simulation code for this is not so hard. Actually, what might be the hardest thing if you want to simulate a protein is you need to get all these different coefficients. So here I haven't even written that this epsilon and sigma depend on I and j. So the charges depend on the particle index, but also the coefficients here, and all these force constants depend on the atom types involved. Yeah, so you need to have a force field. You need to read in all those hundreds or thousands of parameters and then pass them to the right atoms here. So that's actually more work than writing the force derivation itself here. More here? No, let's stop here for the break, I think. So this was a very short introduction on how the model looks like. Then we get, after the break, we'll go in more detail on how it's used, what considerations are there. Are there questions here about the model? It's quite quick, but I think several things were already covered in earlier lectures. So in the labs, you'll use GROMACS and all these. This computes all these things for you, and the parameters are automatically passed through. You just choose which force field you want, and the code does everything for you. Luckily, it's very easy to make bookkeeping mistakes here, as you can imagine. So to be careful and carefully to test your code and test the force fields. Okay, time for a break then. Oh, je måste vara lite. Okay, so there are several questions about the labs and attendance there. So the attendance is obligatory, I just checked. Since you do not have to write a report, but you'll be asked questions there. So, but if you can't, if people really can't come, they would have to write a report. But it seems like some people have overlap, so then they can likely you can report in later. You can work on it earlier, or maybe you can finish the things in the 2 hours that you have there. So, if people really can't come, they should tell us, and then we should ask some kind of report. But the idea is that people sit there and you can work, and we'll ask some questions while people are there to not have to write reports and correct. Yes? Yes. You might not need all 4 hours on both, but you should be there so we can see that, we can discuss and see that you understood everything. Okay, so let's continue. So we discussed the model now, how it's set up. So now we go back to Newton's equation and the integrator. So we now can get the acceleration from the force divided by the mass, and then you can integrate this. But there are errors here. So still, even if the integrator is symplectic in this system, so you have energy conserved, still the system is going to be chaotic. So this is again something which is a bit beyond this course. This is handled treated in some other courses, like my simulation and modeling courses. There are more courses on this on Hamiltonian dynamics. So the basics here is that if I have a Hamiltonian system with many degrees of freedom, then it's likely going to be chaotic. It's not guaranteed, but it's very likely. So and here we have obviously easily 10,000s, 100,000s of degrees of freedom. So the system is chaotic. And this basically means that if you do 100 steps or so, then you can see differences up to, very, very significant digits in some results. So if you want to follow the trajectory of an individual atom, then it's very difficult to get that very accurate in this way. Or at least you could get it accurate, but you have to do a lot of effort. That's not what these codes are usually optimized for. So even if I compile, for instance, the package with different compiler flags or different compiler, you get different results very quickly after 100 steps or so. You can see significant differences. So the question then, is it even possible to simulate here? Because the results are different. I mean, we often get these questions like a system administrator is installing GROMACS on some compute center somewhere, and they run, and then they run with a different compilation setup or so, and say, the results are different. I mean, this is unreliable. But this is very different from something like quantum mechanics or so, where you want to calculate one number very accurately. So here, we're not interested in tracking exactly where an atom goes. So an example here is a good example is you might want to try to track a single particle going through the air, so a single oxygen molecule or so going through this room. Yeah, it's extremely difficult to predict where it goes exactly, because it collides with many other molecules around as it goes around. So there are extremely many collisions. So if you want to track one molecule, it's going to be extremely hard to do it accurately. You will need to know the positions of all the molecules and the velocities extremely accurately, and then you need to predict this. But why would you want to do that? I mean, that's completely irrelevant for figuring out how the air in the room behaves, right? You just want to know, for instance, is there airflow in the room or so? But you're not never interested in the path of a single molecule. You're interested in how does the collectively, how does the air behave in the room? Does it increase in temperature? Yeah. Does it expand? Whatever. So, like there, it's usually never relevant where a single atom goes exactly at a given time. What you're interested in is how averages behave in the system here. Does the molecule, on average, open? Does it close? Does it move? Does it change? So, it doesn't matter that the system is chaotic. So this is a problem. If I run a simulation 2 times, I get very different results. So even one simulation is difficult to get reproducible unless you've done enormous amount of effort in your code to make sure that you're not relying on any order of operations. The processor might reorder operations. On a GPU, it's even harder to get this right. We're working on this because for testing, it's of course nice. If you can run the code twice, you get the same answer for testing. Huh? You can imagine. But for physics, it's not so relevant. So then one can ask, what's a trajectory? So a trajectory is coordinates and velocities as a function of time of all the particles that I get out of this. So that's not an accurate prediction of the motion of individual particles in this here. So it's just a representation, hopefully a probable representation of what could happen with the system. So difference in this grow exponentially, so they're very quickly not the same. But trajectories aren't really random either. So an individual trajectory might be random in the sense that it deviates quickly from the exact solution of your model, so to say. But as I said, well, here are shadow trajectories which stay close to the real path for some time to ensure that you conserve energy. But the more important thing is that if I generate many of these trajectories, they follow certain distributions. So, or if I generate a very long trajectory that revisits states. And that goes to thermodynamics, which is again get a bit beyond the scope of this course. So I'll get back to this in a bit more detail in the next slide here. So in principle, this would give a microcanonical ensemble. If you look at Newton's equation of motion, it conserves total energy. But in practice, if the system is large, this converges to a Boltzmann ensemble if you would sample long enough. But we often add a thermostat, as I'll show on the next slide, which anyhow goes towards a Boltzmann ensemble. So this means if my system is large and I simulate long enough, that the distribution of states as a function of the coordinates here, I just ignore the velocities for convenience, gives you a Boltzmann ensemble. So it's proportional to e to the power minus the potential divided by kT. So that's the important thing here. So, and this is often what you're after. I mean, you might be after, I'll go discuss that also soon. You might be after dynamics, but very often you're after what states are relevant in the system. And how does it move between those states, which depends a bit on dynamics, but actually not so much often. So you're after this Boltzmann distribution. Yeah, so that's what molecular dynamics gives you. So then it doesn't matter what one individual trajectory does, as long as you simulate very long or simulate many trajectories, that the distribution converges towards this. That's what you're after. So that's why it doesn't matter that MD is chaotic, at least in these systems. It's different, of course, if I really would want to track the motion of a particle, which is in the air in the room is not relevant. But if I want to track planets, for instance, with the same equations, if I want to track planets in the galaxy, then I would rather have it very accurate, yes. That's a very different goal here. So here we're after the distribution and some kinetics, as I'll get to soon. So that's why it works. So then some words on ensembles. I hope you had this in other courses. So plane MD, if the equation I just shown, it conserves the total energy. So they have a Hamiltonian system, the total energy is conserved. So this would lead to a microcanonical ensemble where the total energy is constant. But since we're simulating very small systems, which are in reality are part of a much bigger system, actually you have exchange of information between the system you pretend you're simulating and the environment around there. So to get a proper Boltzmann ensemble or a constant number of particles, volume and temperature, you need a thermostat. So I won't go into detail how you do that. That's not so hard. You can look that up also if you're interested. So then you get a canonical ensemble, which follows the Boltzmann distribution. That's what we do most often. So I think in the exercise, I think you're probably running this NPT, constant NPT ensemble, or isothermal, isobaric, where you also keep the pressure constant, or at least fluctuating around the average you're interested in. But again, the most important thing here is that you're at constant temperature, so you get a Boltzmann ensemble, so you know how your states are distributed. An important thing here, but I hope you had this in other course covered in other courses, that as the number of particles increases, then all these ensembles converge towards each other. So if the system gets very big, then it doesn't matter if you keep the energy constant or the temperature. It will all give the same distribution. So these differences disappear. Systems here are about on the limit because 100,000 particles or so is still, there's some small differences between constant volume and constant pressure, for instance. But I hope you had the details of this in other courses here. I'll just touch upon this so you see why we use, well, I mean, the important thing is that we want to sample according to this, or maybe have the pressure constant as well, which complicates this slightly, but let's not go into such detail here. And that's why in the exercise next week you'll also use a thermostat and probably a barostat for keeping the pressure constant. Okay, so then let's move towards focus on the applications and what we're trying to do here. So we're sampling a complex landscape often in 3 n-dimensional space where n is the number of atoms. So this is an extremely large system. And the question is then, what are you sampling? What are you after? So the native structure is often a free energy minimum, so it could be the minimum here, but then you have a very complex landscape. And as we discussed with protein folding, I mean, you could start out at the wrong state, for instance, here, and then if this barrier is too high, you might never end up where you want to be. So there's an issue of where you start, and there's an issue of how much you can sample. And that's always an issue here. So this is drawn in 2 dimensions, but the issue here is also that these proteins are, how many amino acids? A few hundred, so that means that they could quickly have 10,000s of degrees of freedom. So there are many, many degrees of freedom to keep track of, so it's very difficult to actually check if something is reasonable, if you know what quality to check for already. So this is a very complicated problem. The combined thing of that you get stuck in these minima, you can't simulate long enough, and it's very difficult to check if your structure is reasonable. So for that you need to have insight in how different details of a protein should look like to actually understand if something is reasonable. Or you have to be lucky enough that the system moves around so fast that you can see that you cover interesting states. We'll talk a bit at enhanced sampling towards the end of the lecture to see how one can improve this situation, because if you end up in a state like this which is wrong, you might actually see it's the wrong state. How do you get to a better state, for instance? Those are interesting questions. Okay, so then we can actually look how does a simulation look like. You'll see that more next week. But here's an example of a single water molecule with time steps. So the time step is 2 femtosecond to be able to integrate collisions between atoms. So you can maybe go to 4 or so for this particular water case. You could push it a bit, but so you see that this is rough. So this molecule goes back and forward because actually there's water around it everywhere. So it's not a single molecule, but I show only one just for clearness. If it would be a single molecule, it would just fly on. So you can see that it bumps and it goes back and forward. So it wiggles a bit and it moves a bit as well. So most of the time simulating is spent with these kind of things just wiggle. Yeah, so you would like to speed up, I mean press the fast forward button, but in simulations you have to do this because atoms bump into each other, so the time step is 2 femtoseconds, so there's no way around this, really. So you're spending most time computing uninteresting thermal motion, and then sometimes something interesting happens. So if you go towards a larger, here's a whole box of these water molecules, so you can see them moving around. So they all wiggle, as you see. Yeah, so there's a lot of thermal motion. So this is really how, well, in reality, of course, there's electrons, and it's a bit more complex than that. But this is basically how water looks like if it moves around. So most of it is just thermal motion, but then one could push on something somewhere, give a velocity or so, you get Navier-Stokes out of this. I mean, everything is here, so you get the full real dynamics. So we actually I now involved in some fluid dynamics projects where we actually compute fluid properties from this. So you can look at surface tensions, you can look at viscosity, you can look at all kind of things. But again, most of the time is spent computing small bumps and thermal stuff. So that's the basics. So a bit more interesting so this is a small protein chain, again in solvent, which is not shown here. So this wiggles around and you see some conformational changes. So this again goes to the phi and psi angles, which is the main things that move here. I mean, apart from the hydrogens that you see wiggling around, or the CH3 groups which can rotate, the main thing is the phi psi angles moving. And the rest is quite rigid. So this is what you get out of, you just do an MD simulation, you get this. So then obviously you need to have an interesting question to make something interesting out of this. So you can simulate something, but you need to have a question before you can actually learn something about the system. Well, here you can of course see, I mean, if you didn't know that it moved like this, you might not have known, then you learn that. But I've watched these things very often, so I know what to expect. Okay, so then actually towards a more interesting real system. So this is, for instance, has been a popular system. Now we mainly use it as a benchmark. So this is a small alpha helical peptide with 3 alpha helices. So there are some interesting residues indicated here. So this is a Villen headpiece. So it's small, so it simulates fast. And how that looks like if you actually have it in a simulation box. So here we've drawn the water as sticks and the protein as balls, and you see it's a blob in this water box, which is periodically connected, which I have shown on a slide later. I have all these duplicate slides here. Let's see what's happened here. All right, yeah. So this is 33 residues, and it's about 750 atoms then, the protein. But then you need to add water and ions, and then you get to about 10,000 atoms in here. I think I've messed up the order of the slides a bit. So you can say it now already. So so actually for a small system, you're mainly simulating water, solvent, yes? So But that's because in reality the molecule is in water. So you could put it in vacuum and save a lot of computational time. But that's of course very unrealistic because the protein interacts very different with vacuum, no interaction, than with water, which is a strong interaction. So you need all the solvent. People have tried to make this more efficient with some implicit solvent, but that doesn't work well. So even for a membrane protein or so, still most of the system is water actually. So you're spending a lot of time on the solvent, but you need to do that since that's the environment that the system is in. Yeah, the order of the slides is a bit strange. Okay, sorry. So here's a list of some programs that are popular in this field. So we are the developers of the GROMACS package, which is probably the most popular by now. There's the others left are all American, except I forgot if ASMD comes from the United States. So in Europe, there are no other packages that have really survived. So there's AMBER, CHARM, NAMD, LAMPS, which is used a lot in the materials science field, not so much biomolecular simulations. ASMD, which is GPU-only code. Then it used to be when I started that all codes were tied to a force field. So when this field started, actually as a PhD student, you would have to write your own ND code, and then every group had their own force field. But yeah, as you can see, with the amount of parameters and the accuracy you need there, that's a lot of effort. So it's better to put efforts together and work on this with people from all over the world. So now, there used to be, AMBER, CHARM, and OPLS used to be packaged in force fields, but now most of these haven't survived. AMBER is still there. CHARM is, still there, but not for long probably. So now there's a few force fields left, like the AMBER and the CHARM force field are the most popular force fields, and they're quite good. And there are a few codes left there. And most of these are freely available to academia. Like GROMACS is completely free. You can even make money out of it if you want to. So it's LGPL. So there used to be codes which wanted to go commercial, but they're basically all lost. If in this field you get bought up by a pharmaceutical company or some company providing tools for pharmaceutical companies, they'll just put a shiny user interface in front of it and don't care about the code anymore. And then you're dead because you can't compete against the developments of scientists that like to do fun stuff. So, which is good, I think. So scientific tools should be freely available for everyone to use. That's a far better situation. There's actually D. Shaw, I don't know if that got mentioned already during this course, the billionaire in New York who has written, he has his own special purpose MD machine. They actually have free code, but they now have a proprietary force field, but I think that shouldn't be allowed to publish with this. So you can simulate, but you can't see the parameters and they can't be published either. So then I think should not be allowed in science. I mean, you can't publish a model where the parameters are secret. I mean, that's ridiculous. So still it gets through in some journals, but I've also been working on policies for PLOS, for instance, journal, for instance, that's not acceptable. I mean, if you want to publish simulations, then you should publish the parameters. You can't do it secretly. Okay, so then how does a typical simulation look like? Well, there's usually goes like get a structure, usually from the PDB file. So this is also what you'll do in the labs. I think the structure is provided there, the PDB file, or the PDB from the PDB database. You often need to fix missing segments and stuff. For the exercise, we of course don't have that, but often in experiments you can't see certain parts of the protein or they're not very well resolved. You need to prepare the topology, so that's basically prepare the model, but there's usually automated tools for this in GROMACS, and many packages have that. Add solvent, then you often need to energy minimize because your model might be crude, your water that you added might overlap a bit, so you need to energy minimize a bit. Equilibrate a bit, maybe keeping some things fixed sometimes because there's still some bit of overlap. You don't want to right away distort your initial state, which might have been good. And then you run production simulation and then you analyze the results. That's basically what there's to it. And most of this is fully automated, except for the fixing part if that's necessary. So fixing can't be automated if there's experimental information missing. Although, well, sometimes it can be to a certain extent. But if there are atoms missing, even GROMACS can do it a bit. But if there are whole residues missing, then you need to do modeling. So this is a very standard flow. So unlike many other fields of science, and especially physics, where you actually have to devise models and play with them here, this is very standard, and that's why there are a few codes which are highly optimized where a lot of effort went into, because this protocol is very standard. The model is standard, there are just a few force fields. Or even if you would use different force fields or different materials, the interactions are still very similar in the force field. So this is all very standard. So that's why there's just a few codes worldwide that are relevant, and there's a lot of effort going into them. So this is of big advantage to the field, that you don't need to worry about this. You just download something, maybe compile it, and then it runs very efficiently. So what you're actually interested in here can differ very much depending on the system, but the flow is usually the same. Okay, so then we go into the troubles here that we have. So one big issue here is that we can currently reach microseconds. Maybe I should shift over the years. This bar should shift, but I don't know if you update the slides often enough. Maybe I should make an automatic update that it shifts each year with Moore's law or so. The bar shifts along. Yeah, so we can do up to microseconds in reasonable time now. So that can be done depending on the hardware you have in a few days or weeks or so of simulation time. Then the issue is that experiments are often on the scales, or here, sorry, it's really, oh, I cut and pasted this from another keynote and all the exponents are gone, sorry about that. So this is 10 to the power 0, this is 1 second, and this is 1,000 seconds. So biological experiments, so we talked about ion channels, so there you have events on the order of microseconds or so. So that's doable with the current time scales. But then there are many experiments which are much slower, like translation and other things which are on the order of seconds or more. So that's where we'd like to be, of course, but that's hard. So we'd like to be a bit further out here where we need to be, because there we have much more overlap of experiments. So it's of course beneficial if you get more information from experiments and we can simulate those time scales. Currently there's often a bit too much of a gap. So you can try to do something, but you're not sure if it's reliable, and so you would gain much more if you're a bit more towards there, where you can cover more time scales and get more confirmation from experiments. But we'll get there. I mean, computers are getting faster, code is getting better, algorithms are getting better. But you see here that there's a massive range here. So the time step is 2 femtoseconds, maybe 4. So here is already a billion time steps, yeah? But that's doable. So code is so fast nowadays, especially GROMACS, that you can do a billion time steps in a reasonable time. So this is interesting because this actually is very different from any other scientific computing I realized over the past decade or so. So I've been at a lot of meetings with other HPC people, HPC meetings, and then our needs here are very different from others. Since we need to do a billion steps in a short amount of time as possible, we can do especially on the GPU on a single workstation or so, we can do 1,000 steps per second, which is a lot if you compare it to other computational problems where you often do 1 step per second or 10 steps per second or so if you do Navier-Stokes or so. So this is gives all kind of trouble because you need to do 1 time step in a millisecond basically. So that's very fast. So on GPUs, we for instance had the issue for a long time, and we still have it to a certain extent, is that this 1,000 steps per second corresponds to 1,000 frames per second. And computer games, for any of you who play, I mean, you know, you're happy. Well, you used to be happy maybe with 30 frames per second. Now it's maybe 60 or so. You want to do 3D, it's 120, but it's still an order of magnitude slower than the 1,000 per second we need. You know? So it used to be that the drivers from NVIDIA, for instance, they would have massive overhead because they didn't care about those rates. So you'd be spending all your simulation time in driver overhead because they didn't optimize it. So now we push them together with other people from NAMD, from the other packages, and Amber. So now they reduced it a bit, but there's still an issue. So we can't go much faster than 1,000 steps per second because the overheads are high, which is just stupid driver overhead from NVIDIA. But so there are many things like this. There's MPI issues, there's OpenMP threading issues. That's because basically almost no other code needs this high iteration rates. And that's because we have this sequential problem in MD that everything is sequential. I mean, you need, in this integrator, you need the previous time step computed, the previous coordinates to do the new ones. So we're stuck with that, apart from tricks, as I'll show soon. But still, there's a high need to push this down. So we're getting close toward a limit now, I think. So the compute power still goes up of CPUs and GPUs, but getting this time down is hard. So we can maybe compute bigger systems, but not compute faster. So yeah, how do we accelerate then? So one thing you would think is take bigger time steps. That would certainly help, but then there's the issue with atoms bumping into each other. So we had some tricks of this in GROMACS, which goes beyond the scope of this lecture. Now we can do multiple time stepping, which is popular, so we're working on that as well, but that gives you at most a factor of 2 or so. Using fewer particles might help a bit. And how do you do that? Because you don't want a too small solvent layer. But you can make a more spherical unit zone. So instead of a cube, you can have a rhombic dodecahedron. I don't know if that's actually used in the exercise, but it helps a bit. Other thing is simulate in parallel, but you get more resources, but that comes at the cost of communication. So we're going the other way around. So we have GROMACS was from the start parallel, which was the first thing. I think it actually stands for Groningen machine for chemical simulation. So there was a hardware machine as well in parallel, which was one of the first. So we were very early parallel, and then the parallel wave came with all parallel computers where other codes had trouble, but we could use that. But now it's actually the other way around. So since GPUs and CPUs are getting so much bigger, at some point it doesn't make sense anymore to go parallel because our problem sizes are fixed. I mean, a protein is a protein. It's always 100 amino acids, 200, maybe there are several units, it's 500, but it's never, you cannot say, just make my system bigger, 10,000 residues, 100,000. It doesn't work. Like with Navier-Stokes or so, you can do turbulence with bigger models. So this might disappear. Well, there's parallel inside the node, so there's still parallelization to worry about. So use accelerators, obviously GPUs. I mean, we are very happy with that. So if we can, we use GPUs. Unfortunately, the supercomputing center here has almost none. But if we buy machines for ourselves, we fill them up with GPUs. Especially gaming GPUs are very cheap from NVIDIA. If you need to buy supercomputing GPUs, they're a factor of 10 more expensive. So, and they're slower. So not so nice. But we don't care. We can buy what we like still. Then there's coarse graining. So that's instead of looking at individual atoms, I can look at groups of atoms, like a residue one atom or so. So that has been popular for a long time, but that makes the model far less accurate and much less predictive. So you have to be very careful. So this was a popular wave, a decade ago or so, but I think it's losing importance now. Also because actually, it doesn't gain you so much anymore with the modern hardware. And we're getting much faster. So yeah, these topics are all covered in my advanced molecular dynamics course which is a PhD level course, which I'll give in May. Let's see what happened to the order here of the slides. I messed things up. Yeah, sorry about that. Is this important? Yeah, no, let's skip that. Yeah, environments I touched upon already, so that's it's not realistic to simulate a molecule without solvent, because in reality there's solvent, so you need to take that into account. So then there's quantum chemistry often tries to model water as a continuum in space, like a dielectric constant or so, which might be okay if your structure doesn't move much, but here you have hydrogen bonding, you have all kinds of effects. So a dielectric coefficient of 80 doesn't represent water really. So then there are more advanced implicit solvent models, which reduces the number of atoms significantly, but they are not very good. So, and they're actually slower. On modern hardware, it's much more efficient to do repetitive, stupid things the same all the time, like the Lennard-Jones and the Coulomb interactions, which are simple. Work better than this complex thing with complex indexing to keep track of densities of your solvent. So we use explicit solvent. Then, let's have a look at how we actually make a force field. So there's critical parameters, so there's we have Bond's angle, so the equilibrium distance, and the angle determines roughly how the structure looks like. Not so much the force constant doesn't matter much here. So the dihedrals, you want the potential minima and barriers correct for the transitions. Let's see the partial charges for each atom. You want very accurate, the Lennard-Jones parameters, and are different for each type. So I think sorry about the order. This is a bit messy now. We covered most of this. Yes, so maybe interesting here is an extreme example which I encountered when I was a postdoc at the Max Planck Institute for Polymer Research in Mainz, is that this is an experiment that you can do. If you actually mix polymers and you have hydrogen, normal hydrogens, and you have deuterated some of them, that's a very subtle effect. So there should be about the same hydrogen and deuterated hydrogen. But then they phase separate. That's just because all the polymers, all the interactions add up. So they're not randomly adding up, but they're all the same, right? If I have one of these and one of these interacting, then suddenly versus hydrogen with hydrogen or deuterated with deuterated polymer, then all the interactions over all the polymer add up. So that's a worst case of errors adding up. But you have the same thing in a force field here. So that's why force fields need to be very accurate. So how we make a force field nowadays is we systematically take bonded parameters from quantum mechanics. The partial charges are fitted also from quantum mechanics. The electrostatics is then fitted on the surface. Then the Lagrange parameters, which are already inaccurate as we described as a model, so you just fit it to density, heat of vaporization. So here's an estimate of the amount of work needed for this. So for 2 ions in water, which I have done, if you want that very accurate, and it takes a few days, so I can do that by myself in a few days or so. That's doable. A polymer might take a few months, and then a whole protein can take a few years of a whole group. So that's basically the amount of effort going into this. So this is where the quality of your simulation comes from, which is all this work. So that's what you need to look out for. And there's always a discussion if you see something interesting, if you can simulate longer, is it real or is it an artifact of the force field? Yeah, so this also comes into this timescale thing. So initially here we could simulate only up to here or so, and then proteins fell apart. We realized at some point when we could simulate long enough, so then you make the force field a bit stickier. Huh? But then you could simulate a bit longer, and then you realize proteins collapse, or they don't go to interesting states, and then you have to make it a bit weaker again. And so as timescales increase, as computational power gets more and the codes get faster, you realize more and more issues with your force fields, more subtle issues. So currently, I think we're in the regime. I was talking with a colleague, former colleague of mine, or who was still a colleague who's now in Germany. He said that for membrane protein simulations, the right time is about this or so. Then up to here, your results get more accurate if you compare them with experiments. But if you simulate longer than a microsecond or longer than a few hundred nanoseconds, then they get worse again, because then you see the errors of the force fields coming up. So then the system can diffuse away to artificially or lower free energy states in the model, which are not actual lower free energy. Yeah. So, but that point will usually be roughly on the time scale you can reach currently, because if people realize these errors, then they start improving the force fields again. So there's always this reliability issue, and that's why it's so important that people do all this. What was it now? All this work here. So although it's a bit unthankful work for individual PhD students, apart from your publication hits going up, it's very important that this still is done. Boundary conditions we discussed. Yes, I think it is just duplicate. Yeah. So one interesting technical thing is, I just have duplicate slides in here. Sorry about that. Yeah, I think my fever it didn't help me in ordering the slides. I have all the information I want, but some things got duplicated. One trick is periodic boundary conditions. So you could simulate a protein in a solvent shell like this, which some people still do, although that's a very old-fashioned setup. What you get then, if you would just have vacuum outside this, you get a high surface tension on this edge because you get a droplet. So you get surface artifacts. Also, the electrostatic interactions would be strange with you would get an electrostatic boundary or dielectric boundary here at the edge. So to avoid such things, the simple trick is to use periodic boundary conditions, which is a Pac-Man-like thing. I don't know if Pac-Man is still played in these. You still know about this thing. So if you hop over a periodic boundary, you come in on the other side. So basically, your simulation cell is this, but it's surrounded by identical copies of itself. And that means if this atom 1 here has to interact with atom 2, actually the shortest distance, or the distance within the cutoff that I use, is this one on this side. So you compute the interaction with this one. Yeah, that's how this works. And then if atoms move out, well, if they move out, you could put it back or not put it back. It's the same as long as you compute distances correctly periodic. So this works fine as long as interactions have finite range. Then Coulomb interactions have 1 over r decay, so that's very slow. So actually you can't do that there, so you can't cut it off. So then you need to, what we do there is we have a method called particle mesh Ewald, which computes interactions of each atom with all the periodic copies of all the other ones. That's infinitely many. That turns out to be the best way to do it, the most accurate. And it's actually, computationally, it's also not so bad. So that's what we do there. That's also what you'll see in the tutorial. So this is a very convenient trick. It can be sometimes a bit difficult in terms of visualization and interpreting the results, but that's it. This slide we had before. This slide, yes. So yeah, then what can we actually do with MD? So molecular dynamics is called dynamics, but actually you're often just interested in the Boltzmann distribution to get out of it. So one thing is, for instance, structure of liquids, crystals, polymer melts, or proteins. So if you're just interested in what's the native state or what's the stable state. You could look at structure of interfaces. You could look at distributions of ions in liquids, which is also interested for proteins. Where are ions distributed? Where are other molecules distributed? Structural fluctuations of proteins and polymers. So this is still not the dynamics. You could just be interested in how wide is the ensemble, how wide is the distribution. And then phase diagrams, but that's beyond this course, but there Monte Carlo is better. For many of these things, you still use molecular dynamics is the best way of getting there, even though you're not interested in dynamics. Because it's an efficient way to sample. So here's one example from our or actually a small company working or sitting on our floor. They're looking at skin. So this is how your skin looks like at a very detailed level. So they're interested in getting actually medication through the skin, but you can look at molecules, see how they behave and how they look like to see what would be a barrier of drugs going through your skin. And then you can actually measure dynamic things by pulling the drugs through, but that's what they're trying to do. Then if we look at dynamic properties, then yeah, you can look at some basic things for liquids like diffusion, viscosity, dynamics of phase transitions. But for this course, it's like finding out how proteins work in our bodies. That's very often you want to look at some conformational transition. Or how drugs bind to proteins, for instance. How does a drug get in? Does things need to move open first? In what sequence do things go? What's the rate limiting step there? How do I need to modify the protein to make, or the drug more often to make it bind better? These kind of things. Liquid spreading on surfaces is another thing I look at. That's not the topic of this course. So that's here you actually use the dynamics part of the molecular dynamics in your analysis. Okay, so let's get to the topic of as a last thing, the topic of last lecture, also studying conformational transitions. So very often you're interested in a membrane protein having maybe two states, an open state and a closed state, or so. How does it move between those? And experimentally, you might just have one state, or maybe the end states, but then still you might not know how it moves between the two. So the question is then, I maybe know one state here and one state there, or maybe only one, and how does it move between the two? Or maybe what's the other state if I only know one? And then the issue here is that this free energy landscape is very rough. So this is, again, it's just an artist's impression. But it's not as simple as I take up the direct route over here, since then you might go over this very high barrier. Whereas the realistic pathway, you might find something like this, but maybe the most probable pathway is this one, which takes the lowest barrier here, but maybe a few. So this is an extremely complex problem, since you don't know how the landscape looks like, and there could be many barriers, and the best route might not be the straight route that you might lay out. And you don't even know how many dimensions there are here that are relevant either. And this process can be very slow, because there could be very many minima here, or there could be some barrier which is quite high, and the rate goes down exponentially with the barrier height, like Arrhenius kinetics. So how do you do this if you can't reach the timescales that you need to have, the timescale of the event here? So I'll discuss basically one technique, or quickly touch upon a second one. So since we're doing simulations here, so we have the distribution is the Boltzmann distribution here. So now written in a slightly different way. I have beta and u instead of kt and v. But the trick is that since we're doing simulations and we have full control over the model, we can do whatever we want. Yeah, so I could add a bias potential, which I call W here, and I could make the landscape with this high barrier where the system is stuck here and never crosses. I could make it look like that, for instance, and the thing would just go back and forward. Yeah, I can fully do that if I know how to do that. Yeah? No problem at all. Then you say, well, the results are now very different since I have a different potential, which is of course true. But you can correct for this, since now I have a new distribution rho prime, but it just differs from the original one by a factor e to the power minus w. So I can get back my original distribution rho just by multiplying rho prime with e to the power beta w. Yeah, that's trivial even. Yeah, so if I roughly know how the barrier looks like, I can completely remove it and sample very fast. And even get a lot more sampling at the barrier as well. The kinetics of obviously is going to be off, but you get all your distributions you can get exact. Yeah, so this is extremely powerful if you know how to do this. Yeah? So if you look at a normal simulation, this is very often what happens. So you're just waiting there. So maybe you're simulating for a few hours, nothing happens. You simulate for a day, you simulate for a week, and then you think like, yeah, how long should I wait? Should I wait another week or another few weeks, burn more compute hours on the supercomputer, or do something. Yeah. So this is, you might be lucky or not, but you don't know how high the barrier is, so you don't know. Yeah. So the ideal case would be here if this is the barrier and I can add a bias potential which exactly makes the thing completely flat. That would be ideal. But then you need to know how the barrier looks like, and if you know that, you wouldn't be doing this because you would already have your answer. So that doesn't work. So you need some method there. So I had a PhD student working on a method which does this automatically, which is called the accelerated weight histogram method. So this is magic. So you'll see here that the system samples around and it adds a bias potential as it samples. So it feels it doesn't get out somewhere. It samples a lot in one point, so then it adds a bias potential there. And you see that this blue line which it generates will converge towards the black line, and now it moves over very often. Huh? So now it's still a bit stuck here because it doesn't have the barrier fully correct, but then it goes back and forth. So now the effective potential of the one minus the other is nearly flat. Yeah? The system just goes back and forward. So that magic just works. You don't need to know how your barrier looks like, it will do it for you. Which sounds too good to be true, which is, yeah, so there's a catch here, but so even better here, I could add, it's the same movie again. I could add multiple walkers here. So now I have, how many do I have? Oh, they're going too fast. I have 8 simulations, I think, yeah? Now it goes much faster, and it's even parallel here. This is nice. Yeah, so I can solve my problem in parallel even faster. They go actually super linear acceleration here. So with 8 walkers, it goes nearly 16 times faster. 12 times faster, I think, or so. So this is really nice. Yeah, it's near perfect match here. It doesn't actually need to match perfectly since you know what you're biasing with the blue, so you get your distributions exact, no matter what. Yeah, so this seems very nice. So now we have solved our problem. Black slide. Where? Oh, sorry. What happened here? The slide is on my screen. Come on. Oh. That's strange. I see it here. Okay. Sorry. That's a technical issue here. Okay. Here it is. Yes. So the thing here is to actually make this work. What you need is this coordinate I drew. Yeah. So you saw this barrier along some direction, but you don't know which direction to take. That's the issue here. So if you know what direction to bias, then we have tools that do it. We have our tool that I showed, but there are other tools around there as well. But you need for that, what you need is a good reaction coordinate, maybe one-dimensional or multi-dimensional. So you need to know along which direction do I need to remove barriers, and that's not easy to find out because you have a very complex big protein. And what should I do? Yeah, so if you're very lucky, it could be easy, like if I need to pull the helix up and down, like Lucy showed. With the field, maybe I can just pull on the helix. But in practice, that tends not to work because you apply a large force and you need to do it much more subtle. So actually identifying the good reaction coordinates is the difficult problem here. So once you have one, then there are automated methods to do this. Here's one example we studied, which is rather easy. So if you want a base pair flipping out of DNA, then it turns out that this hydrogen bond distance is a good reaction coordinate. So that's an easy case. But for instance, this voltage sensor in this membrane protein that Lucy showed is much harder. We have a PhD student that's worked on that for 4 or 5 years, and other PhD students as well, and we still haven't solved that optimally. So that can be very hard. Then a quick note on Markov state modeling. So that's another trick here. So instead of lowering the barriers here, you have kind of a similar trick, but in a different way. So here you build a kinetic model based on transitions. So you can see if you can observe transitions, then from that you can know the relative probability of 2 states that you have the transitions between. So then you first need to identify the Markov states, the states without memory, which is not trivial, but it's doable. And then you can optimize the sampling by simply not revisiting states that you've already seen. So if you go to a state you've seen often, you just say, I stop here. I put my effort somewhere else. That gives you the same kind of benefit, but in a more automated fashion. This can be massively parallel, so you can have thousands of simulations here as you do it smart. So this is actually what's being used here for this case here. So here, they've identified states, and then some are very populated, like this one, but then you get here very often, but you say, if I get there, I don't stay there. I put my calculation somewhere else. And you have to correct, of course, for that bias. That works very, very efficiently. So this is for a system with many states is the useful technique. But conformational changes are often between 2 or 3 states, so there this is not so beneficial. So there it's more beneficial to bias your potential in a smart way. So those are 2 popular techniques by now. Okay, so time is over, so we've come to a summary. So molecular dynamics, as you've seen, is a very powerful technique. You can follow molecular atomistic or molecular motion on atomistic time and length scales. That's basically the thing, and that allows you to do very, very many things. So the accuracy of the force field is critical. As we've seen, there's often complementary information to experiments, which is very nice. You can often combine studies, collaborate. And sampling transitions with high barriers is difficult here. So here you need to either modify the barriers I showed or modify the sampling. So there's a lot of effort. A lot of effort in the field is going here now, currently, in terms of research on method things. So there are a few study questions here, not so many, because you'll be covering most of this in the tutorial next week. Then, let's see. Yeah, no material from the book, but there's the exercises to go to this. There are questions? Well, there's time for questions next week, obviously, as well. So, yes.